Right, welcome back to Calc 2. We are going to continue on partial derivatives today. I am sorry for the length. These are almost always long problems. I'll try to remember that when I'm writing a quiz. All right, so let's go sharing the screen here. And we'll just keep working through some of these problems here, okay? So what do we have here? We have f of xy is equal to, let's see here, we have, I want to do f of xy is equal to, we have x squared plus 5y plus 2x squared y squared. And we would like to find all the partial derivatives here, all right, of the second order partial derivatives. So what we want to do is we want to find d squared dx squared. Remember, this is not a 2, this is a funny looking d for partial derivatives, okay? Almost everybody's looks like a 2 though, so that's the way that works. So what is the partial of x with respect to x? Okay, so we take the derivative here, it's 2x. Now 5y, as far as x is concerned, 5y is a constant. So as far as the partial with x is concerned, this term here, this is 0. Okay, and then remember the y squared is considered to be constant. These are two independent variables. We're not dealing with a quotient or a product rule, rather. We're just pushing this aside. We're saying this is 2y squared, and then we're taking the derivative of 2x here. All right, so that's what we're doing. And then let's see here. Do that. Oops. I want to do. So this is going to be equal to 2x plus 4 . Okay, that's 4xy squared. Okay, and now we want to take the derivative with respect to x again. Okay, so we're taking this of d of f dx. This is equal to d squared f dx squared. We're taking the derivative with respect to x. That's going to be 2, and then it's going to be plus. We take the derivative here. It's just going to be 4y squared. All right, that's what we have there. So that's 2 plus 4y squared. 2 plus 4y. Right. All right, now we want to do crisscross. All right. So we already have the derivative, right, of dx. So what we want to do is we're going to take this derivative with respect to y. Okay. So what was this thing? This thing, right, was 2x plus 2y squared. No, 2x plus 4xy squared. That's what it was. So we want the derivative with respect to y of 2x plus 4xy squared. All right. Now, as far as y is concerned, 2x is a constant, so that's 0. 2 times 4, that's 8xy. Okay, we're only taking the derivative with respect to y. That's it. So this is d squared dy dx of f. All right. So that is 8xy. 8xy. All right, very good. And then we're going to do d squared y. Okay. So d by dy of f, and then we're going to take d of dy of this thing. Okay. So go back to the original equation. All right. And this was x squared plus 5y plus 2x squared y squared. Okay, and we want the derivative with respect to y. Well, x is considered a constant because we're taking derivatives with respect to y. So if that's out, we have 5. Okay, and then we have 2x squared. Those are all constants, and the derivative here is 2y. All right, plus. So this is 5 plus 2 times 2 is 4x squared y. All right. So this is df dy. Now, if I want to take this derivative again with respect to y, because that's what they're asking us to do, all right, the 5 is a constant, so that's 0. Okay, 4x squared, that's a constant. And the derivative of y is just 1. So this is 4x squared, right? 4x squared. All right, hooray. All right. Oh, and they want one more, which is going to be the same thing, but let's just double check it for the sake of consistency here. We want to take this derivative, right? This is my df by dy. This was equal to 5 plus 4x squared y. And now what we want to do is we want to take this derivative here with respect to x. Okay, so it's still a second derivative, but it's going to be with respect to x now. So there's going to be 8xy. And what do you know? That's exactly what we got up there. Of course, it's going to be because, these are continuous functions. Polynomials are continuous functions, so we're not going to have an issue. Okay. So there's no discontinuities, no weird stuff going on. I think we did this one yesterday, so let's move on. Second order partials. Let's do one more before we go back to that. All right. All right, let's take a look at it. So this is R is equal to the ln of x plus y. We don't really consider the absolute values so much. So if you don't want to write them down, that's okay. Ln x plus y. As far as taking your derivative goes, it's okay. You can safely ignore the absolute value. All right. Take the derivative with respect to x. So Rx. Well, there's an x inside of your logarithm function. What's the derivative of the logarithm function, right? Derivative of ln of u is equal to 1 over u du. All right. So this is 1 over x plus y. And then don't forget, we're taking partial with respect to x plus y. Again, y, x doesn't care about what y is doing. So that's 0. It's a constant. And we just have to take the derivative of x, which is just 1. So this is going to be 1 over x plus y, which is equal to x plus y to the negative 1. Why am I doing that? Because they want a second derivative. Okay. So we're going to have to take the derivative of this. I didn't want to use product or quotient rule. I want to use power rule. So this is going to be equal to negative 1 x plus y to the negative 2, right? That's the derivative of u to the negative 1 is equal to negative u to the negative 2 du. So we need the derivative of the inside here, x plus y. And this, again, this derivative with respect to x, right, is just 1. So this is going to be negative 1 over x plus y squared. Okay. And then the chain would be 1. All right, so that would be my r double prime here. Okay, so this was negative 1 over, okay, and we'll say x plus y quantity squared. All right. xy, okay, going to be a very similar thing here. But what we're going to be looking at, right? What is my Rx? Right. This was 1 over x plus y, right? Which is x plus y to the negative 1. Now I'm going to go ahead and take the derivative with respect to y. So we have negative 1, right? Because it's still the reciprocal function. X plus y, negative 2. And then we need the derivative with respect to y of x plus y. Fortunately, in this case, that's still 1. So this is a very nicely boring derivative we have to take here, isn't it? So this is going to be negative 1 over x plus y squared. Okay. So we're going to have the same thing, negative Now we have a fraction 1 over x plus y squared. All right. Lovely. Okay, we take the derivative the other way around. Okay, I don't think anybody's going to be too surprised. Okay, it's the same thing. 1 over, for two reasons. One, the derivative is pretty nice to go through, and part two, we know that the derivative of x then y is the same as derivative of y then x. Okay, so we know that, so we'll check. I think this is one of the few times where it's like all the second derivatives are the same. I mean, this is not a usual thing. Okay, so if we want to do r of y, right, that is 1 over, right, because again, the derivative of the logarithm function is 1 over u du. So it's 1 over whatever's in here times dy now, x plus y. Again, x does not care what y is doing, so that's a constant. Okay, so we just have derivative of y, which is 1. So we have 1 over x plus y, or x plus y to the negative 1. I want to take this derivative again with respect to y. We end up with chain rule, right? So that's negative 1 comes down in front, x plus y to the negative 2. And then we have to deal with our chain. Okay, this is x plus y. X is constant, y is derivative of y is 1. So negative 1, x plus y to the negative 2. All right, so negative 1 over x plus y squared. All right. So why did I go out of my way to write it in this way rather than the easy way of, like I just got done with the calculus problem? Well, you are often going to be giving this result to somebody else, and chances are they are not as good at math as you are. Okay, so you want to give them this information in a way that's going to be useful to them. So giving them this isn't always going to be an effective mode for them to understand. Giving them this idea, though, okay, that's something that somebody could plug some numbers into and get some ideas. So even maybe they haven't had calculus, maybe they had college algebra and they forgot most of it. Okay, so give them something, give them a way to get your numbers easy. Okay, don't fight with them. I see this on the internet all the time, like 6 divided by 2, and then 1 plus 2, like that. And first off, it drives me nuts because there's a couple ways you could actually do this. But like, this is why we use the parentheses. Actually, we don't have, it's not division, it's this one. They don't use that. They use this. And with math to text kind of thing, did you mean this? Is that what that fraction sign means? Or does it mean this? Because it means this, we get 6 divided by 2 times 3. The division sign comes first, so that's 3. 3 times 3 is equal to 9. But if you meant this division as a fraction, and I don't know what the heck you meant because you didn't use a parentheses, then this is 6 over 2 times 3, which is 6 over 6, which is what? Your choice. Okay. It all depends on what did you mean by this divisor. This slash here in type is a little ambiguous. So we wouldn't want to do that to somebody, right? We want everybody to be able to get the right answer. So the way I would phrase these on the Facebook is arrange the parentheses to get the answer 9, arrange the parentheses to get the answer 1. Now it's an interesting problem, or now it's a good problem because it forces people to, like, where do I put the parentheses to get the answer I want you to get? Okay, so kind of depends. which number was this? This was question 9. So let's look at 11. Timer up. I'm sorry, I did not do that. Oh, let's see here. Oh, this one looks delightful. I'm so sorry. We have f of x, y, z is equal to 4x to the 5th plus 3xy minus 2z to the 4th. And they would like us to know all these different things. So we want to find the first partial with y, first partial with x, first partial with z, and now we want yx. Delightful. All right, fx, partial with respect to x. So we want partial of 4x squared, or 4x to the 5th rather, plus 3xy minus 2z to the 4th. Okay, so stuff with x's in it gets to our derivatives. Okay, so this is going to be 20x to the 4th. Take the derivative here, so that's going to be plus 3y. Now z, x doesn't really care what z is doing. So z is considered a constant, a derivative with a constant that's 0. So there's our answer. Okay, y, that's equal to the partial with respect to y of 4x to the 5th plus 3xy minus, I like this one the most, this derivative, okay? Because y doesn't care about x, so that's 0, right? This is a constant as far as y is concerned, okay? So we have this derivative here. We have 3x times the derivative of y. That's 1. And again, the negative 2z to the 4th, y does not care what's going on here. So the derivative of z, that's 0. Okay, it's a constant. And then f sub z, this is equal to d dz, okay, of 4x to the 5th plus 3xy minus 2. This will be a nice one too. Okay. This first term doesn't have a z in it, 0. Second term doesn't have a z in it, 0. So all we're doing is taking negative 2 times the derivative of z to the 4th power. Okay. I'd like to make this an actual 2 rather than a z. So 4 comes down in front, so that's negative 8 z to the cubed. All right. So there's our 3 answers for the first little bits. Okay. There we go. And what else did they want? They wanted the derivative of yx. So they wanted f of y x. So we want the derivative with respect to x of this thing. All right. So what is the derivative of, what is f of, what is this? Oh, this is 3x. Well, that's 3, right? Because the derivative of x with respect to x is 1. All right. So let's get to it and write these guys down. So we have what? This takes longer than the problem sometimes. 20x to the, did I write 20? 20x to the 4th. Okay. Plus 3y. That one was a 0. With y, it was just going to be 3x there, wouldn't it? Because none of the other terms had anything in them. Right? With z, it was negative 8z to the 3. All right. You don't have to stop at 3 dimensions, by the way. I mean, you can just keep going. I mean, we can't draw it. I wouldn't want to draw this function anyway. But, you know, there's no reason why we have to stop at 3. If you have a system with, like, you know, 8 variables in it, you would have an 8-dimensional system. You could take the partials with respect to any of those 8 of those variables. Good luck. All right, but that's what's going on there. Okay. So let's see. Do we want to do this one? Do we want to just move on? It's got 6 parts. This looks terrible. All right. That was 11. We go 14 here. Okay. Weight loss counselor has prepared a program of diet and exercise for a client that gives the following expected weight loss in pounds per week. C is the average daily calorie intake. N is the number of 40-minute aerobic workouts per week. Okay, so we notice we have daily, and we have aerobic workouts per week here. We have expected weight loss in weeks. So just not saying that we have to do unit conversion, just saying that, you know, it might happen. I want to do. Okay, so when they start messing with units like that, I want to make sure I'm keep paying attention. So we'll say W is equal to F of NC. N equals number of 40-minute aerobic exercise. C equals average daily calorie intake. W equals pounds lost per week. Something you want to do for yourself when you get in the industry, when you get a real job, is you want to kind of test these things out first. Okay. So let's see here. What if C is average calorie intake and N is number of 40-minute workouts per week. So we have our function is equal to 1/10 N squared minus 1/5 C plus 24/23/10. So this is per week, right? So what if, you know, what I'm wondering is, like, if we got a negative number out of here, what would that mean? If we got a positive number out of here, what would that mean? Okay. So scariest show on TV for me right now is My 600-Pound Life. So let's pretend that this person did 0 aerobic exercises, minus 1/5, and average daily calorie intake. Some of those people, they don't need 2,000 calories. Okay, they eat like 20,000 calories a day. So let's just see what happens. Okay, I'm assuming you're gonna gain weight on 20,000 calories a day. Okay, 24/23. It's like mukbang at all times. Okay, and then let's see what happens with this, right? We have, let me pause this and get my calculator back. All right, there we go. So they did no aerobics. They did, they ate 20,000 calories a day. So that's negative 20,000 divided by 5, right? And then we're going to add 24/23 divided by 10. All right. We got negative 3757.7. Is that pounds? Pounds per week. All right. Well, this did something for me. It told me that if you do no aerobics and you eat 20,000 calories a day, you can expect your weight loss to be a negative number, which probably means a weight gain. I don't think I really trust the model for that because, you know, those people, I watched that show and it's like, they only get up to about 600 pounds. They don't get to 2 tons. So I suspect something is wrong. I broke the formula. By the way, that's the reason why I do that is because I used to work at an engineering firm, and it was my job to take all the people that are retiring, to take their information and figure out how to put it in a computer so that the later 20th century and the 21st century people could actually handle, doing all that work that the people that put satellites up for a long time did. And there's some formulas I had that had like, I think it had like a x to the 1/4 in it. And I was like, what if that's negative? And then he just laughed at me because this was like a cost. And I said, the cost never goes down. Okay, it's a government program. We're putting satellites up. The moment we get more space, the moment we get more room, the moment we get anything extra to put on it, we're putting it on. Okay, so it does not make any sense to like have a cost savings, because as soon as you have a savings of anything, you put more on the satellite. But if I had done this before I met with them, that would have saved me some humiliation of them laughing at me. I mean, not much, they still would have, but that would have helped. So let's see here. We're going to go with a 1,200 calorie per day diet. Sounds extreme, but all right. So we have weight is equal to 1/10, and then we have 4 40-minute workouts per week, and that was my N, was 40-minute workouts per week. So it's 4 squared minus 1/5 of 1,200 calories plus 2423 over 10. Remembering that a positive number means the weight loss. Okay, so let's see. We have 0.1 times 4 squared, okay, 16, minus 0.2, that's what 1/5 is, 1,200, okay, and plus, can I just say 242.3? I know a lot of people are, they're very afraid to like do anything without the calculator, but 2. No, what was this? This was 3.9. 3.9. All right. I like how we don't get a starting weight, but all right, there we go. We can expect to lose 3.9. It sounds like a lot, actually. Even with this amount of calories, that sounds like a lot, but all right. That's what they said. Find and interpret df by dn. Okay, so let's go through and find it, and then we can go ahead and put some words to it. All right, so we want dw by dn. Okay, so dw is equal to 1/10 n squared, so this is going to be twice 10 times n. Does C have anything to do with the number of calories? No. Does this constant have anything to do with the derivative of n? No. So this is just it. It's 1/5 n. Okay, so this is a rate of change. Okay, so without looking at it, without trying to do that, okay, this is, what are the units here? This is if we change the number of aerobic workouts per week, all right, then that is the result that what's going on with the weight loss. Okay, so it looks like the change in aerobic workouts is responsible for 20%. Well, yeah, it's responsible for this kind of this order of weight loss. So we pretty much go from 1/10 to 1/5 for aerobics. So if we add one more, we would expect a little bit better. Okay. So let's see. This was 1/5. 1/5. That's 2/10. 1/5. Okay, or 0.2. And everything else we held constant. So our derivative made that happen. All right. Now, partial derivative is the rate of change of the workouts per unit change in, no, it's the change in weight per unit change in workouts. Okay, because the F, right, this is what we found was df by dn. So that is the change in weight loss per change in workout. Okay, so thank you very much for giving me a clue. The client currently averages 1,400 calories a day and does 3 40-minute workouts per week. That would be, what would be the approximate impact on weekly weight loss by adding a 4th workout per week? Well, right, going from 3 to 4, okay, we would get one more of these things. Okay, we would have one more. So the marginal amount, right, would just be this guy here. So we would expect an additional weight loss of 0.2. I think that's an additional 0.2 pounds. Right, because 1/5 times 1, right? That would be 0.2. And evaluate. Oh, 4th workout. Yeah, really? Yeah, and it's 4. Okay, so that would be an additional. So it's a cumulative effect, I guess. Okay, so 1/5 times 4 workouts instead of 3 would be 4/5, which would be 0.8 pounds, 0.8 pounds. All right. All right, check that one. Did they just not want that? Did they want 4/5? I don't know. So this is incorrect. 3/5. I think it's still 4/5 because we're plugging in by adding a 4th. All right. I think by adding a 1/3, we would get 3/5 of a pound, but adding a 4th, I think we would get 4/5. But all right, I'm not going to argue with them. I already don't like their formula, but that's okay. All right, so now we know. We'll change it. All right, let's see. Accompanying table gives lung capacity for ages and heights for a particular region. Based on the chart, it is possible to conclude that the partial derivative of lung capacity with respect to age and with respect to height has constant values. What are those values? Age in years, height in inches. Okay, so here's our ages. Is this 20, 25, 30, etc. Height in inches. Okay. 60 inches is 5 foot. So we have 4 foot, 4'10", 5 foot, 5'2", 5'4", 5'6", 6 foot tall, and 6 foot 2. All right. So let's see. Partial derivative in lung capacity with respect to age. All right. So what are we doing? Well, partial derivative of lung capacity. We have lung capacity equals this function of age, and what else do we have here? Height. So they wanted to know what? They wanted to know the partial derivative of lung capacity with respect to age. So they want something like this, df by dA. So we're changing the age, we are not changing the height. So what we have to do is we have to look at for a specific height, for a constant height, we have to see what is the change in age. Like how does the lung capacity change when we switch the ages a little bit, okay? So pick your favorite height, okay? So whatever height you happen to be or close to, that's probably the best one to pick, but I guess I'll pick 68 inches. I'm not a woman, but that's close to my height. I'm 5'9", halfway between these two. So it doesn't say which one to pick. So whatever one you picked is probably going to work out. Okay, which means we're going to get the wrong answer regardless. Okay, so 2110, okay. And then we're gonna go from 2185 to 2110. Okay, I just picked something in the middle. Okay, that was my selection criteria. All right, and this is 2185. Let's go down one. So let's go to 2035. Okay, let's pick another thing. Okay, so this was 68 inches. I just want to check to see what's going to happen. Let's look at 60 inches. All right, so 60 inches, and let's pick these three here. Let's pick 2070, 2155, 2080. Okay. So all we're doing is we're looking at a rate of change. Okay, we're saying what's the DA by D or DF by DA. So what I'm going to do, right, is I'm going to go ahead and take the average rate of change between these guys. Okay, so I want to do 2120 minus 2185, and the difference in ages is 5. Okay, that's my H. I also want to do 2035 minus 2110, and my average is 5. Okay, so let's see what happens here. Just curious to see if it's going to be the same number. Like how good does this chart for a calculus class? 185 divided by 5. Okay, so they have negative 15. Right? It does make sense that for a given height, that your lung capacity decreases as you age as a natural sort of a thing. Okay. Divided by 5. Oops, not that divides. Not that, not yet. Let's get rid of that. Equals, and then look at that. Negative 15. Let's see if it works over here. Right, we did short woman here. Right? No, we didn't. We did. Yes, we did. We did 5-foot woman here. Let's see if it works the same way. It's 2155 minus 2070. All right. 22. Yeah. Divided by 5. Okay, I may have gotten my order mixed up here. Minus 2070, 15, 85. Did I write them down correctly? So it's not constant. I'll bet I wrote it down wrong. 2080 minus 2155. Yeah, I would bet that I miscopied that. They're all negative 15. Whatever I did here, please ignore it, because everywhere else it's looking like it's negative 15. Okay. Glad I did more than one, so I'd have something to check against. Okay. So yeah. Okay. All right. Okay. Negative 15 milliliters per year. Partial derivative of lung capacity with respect to height. Okay, so we're holding age constant and we're checking our heights. Okay, so in this case we have age constant, holding that constant, and we are finding the average rate of change for two heights. All right, I'll bet that's a constant too. Sorry, for somebody who's, I study statistics more, and if you get data that is this perfect, like something is terribly, terribly wrong. Okay, so 66 to 64. Okay, so we're going to say 2120 minus 940. So this is what? And again, pick any ones you want. I think they made them. I think they made them perfect here. So I'll just pick two that I can see on the chart. So let's go with 2400 minus 2240 divided by how many inches they're changing. They're changing by 2 inches, right? So let's go ahead and look at that. That's 2400 minus 2240 equals divided by 2. Okay, 80 milliliters. All right, 24 to 22. So we gain 80 milliliters of lung capacity per inch in height. Okay, so we're gaining 80 milliliters per inch. Okay, am I the only one that looks at like metric and English units in the same sentence and says, wow, that's terrible. Okay, so that's what we have. We have 80 milliliters. There we go. So that's what you're doing. That's actually why you've learned, you know, this thing. Because you think that we don't have like nice, you know, you guys are mostly lab scientist people. You're not going to have nice analytic functions. You're going to have like this table, and they're going to say, figure out what's happening when a change happens. So mostly your deal is like, I'm going to be working in Excel to get the, you know, to get these values from my chart, and that's how you're going to apply most of this stuff. Okay, so this is what you're looking at. Right, we're taking the partial derivative, but really this is your function. Okay, this is your two-dimensional function. Okay, so this is, you know, a lot of I suspect a lot of you are going to be doing stuff like this rather than what we're teaching you, which is doing all of this stuff. Okay, but these are the easy problems. When I got to the chart, that's the hard problem. Okay, so I hope that helps you with partial derivatives. I'll stop talking. I'm sorry for the length. It's terrible. And good luck with that. I will be aware to not ask you a terribly long one for the quiz, because there's a lot of places to mess up. So let's try to keep that at a minimum. Okay, that's for me, not for you so much. You too. But you know, when I write the question, make sure it's not going to, you know, there's not a gazillion different pieces to it. All right. So good luck to your homework, and we will talk tomorrow.